Yeah. So hello and good evening, everyone. So today, today we are in the solving session, week 6 of the NPTEL course, NMR Spectroscopy for Chemists and Biologists. So I hope all of you have gone through the week 6 lectures. So I will wait for a few minutes for other learners to join this course. So in the last live session, we had looked into nuclear Overhauser effect, then a few concepts related to Rosie, right? And also we had looked into SPI, that is population inversion. So in today's session, we will learn more about these techniques in more detail, so that this understanding can help you in solving the questions that are in week 6, and also a few questions that were already asked in week 5. Those questions also I will discuss. So I'll start at 6:05 p.m. So let's wait for 3 more minutes. So I hope everyone is able to follow what is being taught in the lectures. So in the week 6 of this session, there is a lot of concepts related to the quantum mechanical principles of NMR spectroscopy. But before going into that part, I will discuss about I will discuss about the inept technique today, and also a few part of nuclear Overhauser effect was remaining. So I will discuss that first. Yeah, so it's already 6:05, and I'll start today's session. So just a second, I will present today's slides. So I hope the slides are visible. Yeah. Okay, so let's start today's session. Hello everyone. I am Akash Jyoti Pathak. I am a I'm a PhD scholar in the Department of Biosciences and Bioengineering in Indian Institute of Technology, Bombay. And I am a PMRF TA for this course, NMR Spectroscopy for Chemists and Biologists. Uh, uh, so yeah, so I will take up. So today we will discuss a few questions and also look into the concepts in more detail that will help you understand that will help you revise the concept and also understand understand the topics that are being discussed in greater detail. Okay. Okay. Yeah, so in the last session, we were looking into nuclear Overhauser effect. So we what we So in nuclear Overhauser effect, what we learned is that this technique is a nuclear Overhauser effect. It is a it is a very important technique tool for chemists and biologists. And this technique is very important because it has helped in determining the structure of several macromolecules like proteins, nucleic acid, and at atomic resolution. And this so understanding this technique is very important. So what we had learned in this technique is that in nuclear overhauser effect, so there were we were discussing about two spins, A and X, and what we were doing that we were we were perturbing the nuclear spin of one nuclei. We were perturbing the spin of one nuclei, and we were looking into the effect of this perturbation on the other nuclei. Okay, and we also studied that this nuclear Oberhauser effect arises due to dipolar interaction. So as we know that the nuclei behaves like a dipole, right? The nuclei behaves like a dipole because of the because as we have seen that the nuclei contains both protons and neutrons, and having a and these protons being positively charged in presence of a magnetic field, a dipole is generated, and a dipole is generated. In presence of this magnetic field, each nuclei behaves as tiny magnets. And now the so if we have two spin, for example, we have A spin and X spin. Now, so how these spins are oriented or located in space. In space, not so that will be how their what is the distance between these two nuclear spins and how they are oriented that determines that dipole coupling results in dipolar interactions. Okay, here we are what we are doing is we are applying a radio frequency pulse to one of the nuclei, and we are seeing the effect of this radio frequency pulse on the another nuclei. So this is a what we had also seen that this is it depends on the distance between the two nuclei. So how these nuclei are oriented in space. So if we learned that this NOE can take place when the distance is less than 5 to 6 angstrom, right? Is less than 5 to 6 angstrom. Okay, so we had what we had looked into is that the nuclear Oberhauser effect. It is defined as a change in the intensity of one NMR resonance line. Is the change in the intensity of one NMR resonance line. NMR resonance line when another resonance line in the NMR spectrum is perturbed, right? So we have seen the definition of nuclear Hauser effect, that it is the change in the intensity of one NMR resonance line when another resonance line in the NMR spectrum is perturbed. And this was given by this equation, that the nuclear Hauser effect of nuclear spin I when the nuclear spin S is perturbed is given by I minus I naught by I naught, right? So Ni of S is what? So the nuclear Oberhauser effect, that is the enhancement of nuclei I on perturbing nuclei S is given by I minus I naught by I naught, where the NIS is what? It is the NOE at resonance I due to perturbation at resonance S. What is I naught over here? So I naught is the intensity of resonance I in the absence of perturbation. Okay. So we had looked into off resonance, and we had looked into the concept of off resonance and on resonance. So in off resonance, what we are doing is we are applying the frequency applying a RF frequency which is very far away from the frequency of the spins, from the frequency of the spin. So I naught is the intensity of resonance I in absence of any perturbation. So since we are applying the RF pulse, which is very much, which is whose frequency is at a larger whose frequency does not match the resonance frequency of this spin. So I naught is called the what is I naught is basically the intensity in absence of perturbation. Okay, so we had looked into that. This I naught is the resonance, or not resonance, the intensity. Okay, intensity of resonance I in absence of intensity of resonance I in absence of any perturbation, in absence of perturbation. Okay, of resonance, and I is the intensity after perturbation at S. Okay, so for example, this is the I resonance frequency of the I nucleus. This is the S frequency of the S nucleus. So I naught is the intensity of the resonance in absence of any perturbation. So we are applying a frequency which is quite far away from the resonance frequency of the spin nuclei S. So that is I naught. What is the intensity that is obtained? That is I naught. And what is I when we are applying a frequency which is near to the frequency of the S nuclei, then the intensity that we get is called I naught. Okay, so I is the intensity in presence of the after perturbation at S, and I naught is the intensity in absence of perturbation. Okay, so just a second before going into this detail, what I'll do is I will just add a few more slides. Okay. Okay. So what is the perturbation? So what is basically the perturbation is basically the continuous radio frequency pulse, right? It is a continuous radio frequency irradiation. It is the continuous radio frequency irradiation, or it is the radio frequency pulse. Okay. So now we had looked into the steady state NOE and the steady state NOE and the transient NOE also. So we in the steady state NOE, what is done? So in the steady state NOE, this is a low power RF. Okay, this is a low power RF, and This is the FID that we detect. Okay, so this is the standard experimental scheme for obtaining NOE spectrum, and this is the experimental scheme of steady state NOE. And so here, what is done in steady state NOE is that the RF perturbation is continuously applied for a period of time at resonance or at midpoint of group of resonance. Okay, so this low radio frequency power is applied continuously for a period of time. For a period of time, it is applied at resonance or at the midpoint of group of resonance. So if there is peak splitting, if we are seeing a multiplet, then the radio frequency is applied at the radio frequency pulse is applied at the midpoint of group of resonances belonging to the multiplet of spin, and then a 90-degree X pulse is applied. Okay, so what happens when this low radio frequency power is applied for a long time? This causes the spin system to reach a new equilibrium distribution of the population of different energy level. Then the state of the system is monitored by applying an observed pulse and recording the spectrum. This spectrum is called the on-resonance spectrum. So when this radio frequency power is applied for a very long time, it causes saturation of the population in the two state. So if there are two states, for example, there is so we had looked into that. There are so for two spin system, for example, AX system, it will have four different states. It will have four different states, right? So what will be the four different states? Alpha alpha, alpha beta, or consider this beta alpha, alpha beta, and beta beta. Okay, four different state. So now when this so here this is the transition of. So here what is happening? So this is the alpha alpha means this the A nuclei is in alpha state and the X nuclei is also in alpha state. Beta alpha means that the A nuclei is in beta state and the X nuclei is in alpha state. Beta beta means what? Beta beta means that the A nuclei is in beta state and X nuclei is in beta state. And alpha beta, this is again, so this the first state is for the A nuclei and the second state is for the X nuclei. So here in this case, what you are, so these are given by different probabilities. Omega 1, so these are omega 1. Okay, and this is omega 2, omega 2. So what is omega 1? Omega 1 is the single quantum transition, right? Omega 1 is the single quantum transition. Omega 0, what is omega 0 or omega naught? Omega naught is the zero quantum transition. Zero quantum transition and omega 2 is the double quantum transition. Is a double quantum transition. So is it called single quantum transition? So it is called single quantum transition because we are seeing that the state of only one nuclei is changing. So this alpha, this X nuclei, its spin state is remaining same, but the spin of this A nuclei changes. It changes from alpha state to beta state. Okay. Similarly, so you can consider that this one and then. Similarly, in this case also, only the state or the state of one nuclei is changing. That is the alpha state is moving to the beta state. The A state is the alpha state of nuclei X. It remains in alpha state, but the X state changes. So this is the single quantum transition of nuclei X, right? This is for nuclei X. This is for nuclei A. X. Similarly, for this case, this is for A and this is for here. This is for X, right? Okay. So these things we had already seen. Now, yeah. So what is happening is that so when we are applying a low radio frequency power for a very long time, it is causing it is causing the population of the nuclei to become saturated. So there will be equal population in both the state. Okay, in both the state. And now where now what happens? So we are saturating the signal that is coming from one nuclei, and then we are checking the signal that is coming from the other nuclei. So once this is saturated, you will not observe any signal coming from the A nuclei, because you have saturated the population in the alpha state, and in its two states, that are alpha state and beta state, in its lower state and upper state. So there is no population difference in this. And then you are applying a 90-degree pulse to see that what is the effect of this on the X nuclei. Okay, so that is basically what we had discussed. Mm, just a second. Yeah. Okay. Yeah. So just a quick recap. So, so this is off resonance, and Hello. Hello.
Hello.
Hello. Yeah. Yeah. Am I audible?
Yes, now you are audible.
Oh.
But
So
before 10 minutes ago, you are not able.
okay. Okay. Yeah. So we were calculating. Just So we were calculating the so when these when relaxation after perturbation, when relaxation is taking place, what is the how is the population what is the rate of change of population we were calculating. So for dp4 by dt we can what we can write. So you take the help of this will be what it will be w1a plus w1x plus w2 p4 minus p4 naught plus plus w1a p2 minus p2 naught plus w1x p3 minus p3 naught, and this will be w2 p1 minus p1 naught. Okay. Now this the magnetization of spin A and X are related to populations 1 to 4 in this manner. MA naught, it is the magnetization of spin A in equilibrium. It is proportional to half P1 naught plus P2 naught minus P3 minus P4. So why is it so? Because if you see the four states of the AX weakly coupled nuclei, so it can this one was P1, P2, P3, P4. This is alpha, alpha. This is what I had kept this. No, it's beta alpha, right? Beta alpha. This is beta beta. This is alpha beta. So this is the transition probability of first order single order transition of X nuclei, right? So no, A nuclei. So this is A nuclei and this is X nuclei. So W1A, this is W, this is also W1A. This is what? This is W1X, W1X. Okay. So for MA, the magnetization magnetization of spin A can be, is related to populations 1 to 4. How is it related to population 1 to 4? So if you add this P1 plus P2 minus P3 minus P4, and how is this related to MX naught? So for MX naught, what you can for MX what you have to see, this one. Okay. So for MX, what you will write, it will be half P1 plus P3 minus this one X minus P4 minus or minus P2 minus P4. Okay, so for X you will look at these transitions. So P1 to P3 and P2 to P4. So for P1 to P3, this will be this will be what P1 plus P3 and some minus of P2 plus P4. P2 minus P4. So now when we solve this equation, what we get dMA by dt equal to minus 2 W1A plus W0 plus W2 MA minus MA. So this is this is an algebraic calculation. If you calculate this, you will get these two equations. And from here, what we can write further, we can write further that E. So we can write rho A. Rho A as 2 W1A plus W naught plus W2, and rho X can be written as this one, 2 W1X plus W naught plus W2. Okay. So what is this term that we are getting 2W1A plus W naught plus W2, we are replacing this term, and in place of this we are writing rho A. And similarly for this X transition we can write this as rho X. Now similarly for this one also, this sigma AX can be written as W2 minus W naught. So W2 minus W naught is sigma AX. Now, what are these rho A and rho X? These rho A and rho X are called the auto relaxation of spin A and X. So rho A and rho X are called the auto relaxation of A and X. And what is the sigma X called? This is called the cross relaxation. Cross relaxation of A and X. Okay. Is it clear? So whenever they are relaxing after perturbation, when these nuclei are relaxing, there are two types of relaxation that comes into play. One is the auto relaxation rate and another is the cross relaxation. So this cross relaxation is the difference of W2 and W naught, omega 2 and omega naught. So what is omega naught? Omega 2 is the omega 2 is what? It is the, so just now we had seen double quantum transition. Double quantum transition means both these states are changing. Alpha alpha is changing to beta beta. So this is double. Yeah. So this is double quantum transition. Double quantum transition minus zero quantum transition, and this factor, this sigma AX, this factor results in two types of NOE. One is the positive NOE, and is the another one is the negative NOE. So in positive NOE, what will happen? In positive NOE, the main transition that is taking place is W2. That this is playing the important role, and in therefore it is positive. And in negative NOE, the zero quantum transition is playing the main role. So this is having a higher value. That is why it is negative NOE. So what we had seen that for larger molecules, large macromolecules, we have negative NOE. Why for small molecules that are having a small molecular weight, they have positive NOE. Okay. So once this, so now we will look into what is the relation of NOE and correlation time. Now NOE the nuclear overhauser effect depends on the tumbling time tau c. It depends on the tumbling. So in a sample, we have nuclei. We have different nuclei, and these nuclei are undergoing tumbling. They are in continuous tumbling motion. So depending on whether the size of the nuclei is small or large, the nuclei or the sample which has smaller size, then it will show a faster they are always in continuous molecular motion. So tumbling time is they're in continuous molecular motion, and a molecule which has, if it has a lower molecular weight, then it will have lower molecular rate will show a very high molecular motion. It will be in a very fast molecular motion. So the tau c will be very less, right? And for samples which have high molecular weight, those that have high molecular weight, they are in very slow their molecular motions are very slow. So the tumbling time will also be very large for these molecules, right? Tumbling time will be very large. So 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 if a large molecule is there, the it will if a large molecule is there, then it will be it will show less molecular motion and its tumbling time will be high. And if it has low molecular weight, it is a small molecule, so it will have it is in it will show more molecular motion and it will have a lesser tumbling time. And the tumbling time is determined. So yeah, so that is what I was telling, that the tumbling time is determined by the rate of molecular motions. Uh, Rate of molecular motion. And what does correlation time give us? The correlation time gives the time required for the nuclear spin to reorient itself after perturbation. So from why are we considering this concept of correlation time? So this correlation time, it gives the time required for the nuclear spin to reorient itself after the perturbation, and this gives the spectral densities J. So after perturbation, what time the nuclei is taking to reorient itself is the time that it takes is the correlation time. And this these equations, these were already discussed. So you can if you look at this equation, you will see that the omega naught, this zero order quantum transition, this one W1, W6, omega 1, omega 2, they are all related to the correlation time. Okay. So here what you see in this figure is that if a graph is plotted between the nuclear overhauser effect, this signal, this enhancement of signal of nuclei X on of nuclei A on perturbation of nuclei X. That is that and a correlation time is there on the x-axis. We see that it varies in this way. So what we see that for small molecules we have a positive NOE. Okay, for small molecules what we find is as a positive NOE, and for large molecules, they have a negative NOE. The value of they are so starting from 1 to 100 nanosecond, these molecules have from minus 0.5 to -1. They have negative NOE values. Okay. So if dipole-dipole interaction between spin A and X is the sole mechanism of relaxation, then the auto and cross relaxation rates can be calculated by using auto relaxation rate and cross relaxation rate. These can be calculated by using these expressions for transition probabilities contributing to the respective rates. And these are these are the relations that when this auto relaxation rate and cross other than this dipole-dipole interaction, the auto relaxation rate and cross relaxation rate also determines these transitions omega naught, omega 1, and these are the expressions of these transitions. Okay. And what is K over here? K is a constant, and this is also important. K is a constant which is related to this equation. So it varies it is inversely proportional to the distance between the A nuclei and X nuclei to the power of 6. Okay, to the power of 6. So RAX is the distance between the spins A and X, and the other, so so the RAX is the distance between E and X. So all these other terms that you're seeing, they are the normal. This is the Planck's constant. This is the gyromagnetic ratio of A and X. And so this varies as the sixth power. So that is why we had seen that nuclear overhauser is a distance dependent phenomena. So as the distance increases, this one will decrease. Okay. So just remember from this graph that large molecules, what will happen? Large molecules will have larger correlation times. As you can see from this graph that large molecules will have larger correlation times. and small molecules will have short correlation times. So these are for the short molecules. These short molecules have they have short correlation time, tau c. So based on all these concepts, try to solve this question that the spectral density function is a power distribution as a function of frequency due to molecular motion dependent on the spectrometer frequency independent of correlation time representation of the RF power. So in the last in the previous slide, we were seeing about the spectral density function, and the spectral density function arises because of the molecular motion of the nuclei in the sample. These nuclei are in a tumbling motion, and they are continuously undergoing molecular motions. So the larger molecules will have a lesser correlation time, or they will have they are bulky, so they have lesser correlation time, and the larger molecules will have so smaller molecules will have higher correlation time, and this is what we get from the spectral density function, which is a graph that is plotted between the enhancement of the signal and versus the correlation time. So based on this, try to solve this question. So nuclear overall effect depends upon the rate of molecular motion. Why does this depend on the rate of molecular motions? So they depend on the rate of molecular motion since the spectral densities J are dependent on the reorientational correlation times in the system. So what time the nuclei are taking to reorient themselves after the perturbation is removed. Okay, so the first option, it is a power distribution as a function of frequency due to molecular motion. So what do you think about this first option? The first option is right, isn't it? The second option is it is dependent on the spectrometer frequency. So the spectrometer frequency it does not have any role in the spectral density function. That it is independent of the correlation time. So this option is also false because in the previous slide we looked at how these single quantum transition and the double quantum transition, how they are related to the correlation time. So they are obviously dependent on the correlation time. And the fourth is the representation of the RF power. So the spectral density function has no relation to the RF power. So the correct answer is option A. So let's look at the detailed solution of this question. The spectral density function provides a way to understand how different frequencies, the frequencies are also so by different frequencies. So these different frequencies are related to the molecular motions or interactions, and how these different frequencies are contribute to the signal observed. It is a property of the sample. About the now, why are the other options correct? So let's look into these. So it is a so the spectral density function. It is a property of the sample or system being studied and describes the intrinsic distribution of power across frequency. Okay. So just now we discussed that the spectral density function is a property of the sample or the system being studied, and it describes the intrinsic distribution of power across frequency. The spectrometer frequency, it is an intrinsic property, right? Intrinsic distribution of power. So the spectrometer frequency has nothing to do with the observed signal. And the and why is this? It is obviously dependent on correlation time. And about the why is this last option incorrect? So in the last option, we saw that the last option says that it is a representation of the RF power. So RF power has nothing to do with the spectral density function. The The spectral density function is only a measure of how the molecular motions or interactions change over time. right? The correlation time affects how the spectral function is shaped because it influences the rate at which fluctuations or dynamics occur. Okay, so it only depends on the what type of molecule it is. So if it is a large molecule, it will have a very large correlation time. If it is a small molecule, it will have a lesser correlation time. Okay. Okay. Now we will talk about the steady state NOE. So in the steady state NOE, we had discussed the steady state NOE. Since both the spins behave as dipole, it gives rise to cross relaxation and steady state relaxation. And these can be calculated by measuring from the expression of transition probabilities. So this eta AX will be given as mx minus mx naught by m naught x. Now we get this equation eta x. So in steady state, we can derive this equation also. Now for small molecules. So for small molecules, what we had seen that we saw that sigma ax is what? Sigma ax is the, if you look at rho x. Rho x is the sigma x is the cross relaxation rate, and rho x is the auto relaxation rate. So the cross relaxation is given by omega 2 minus omega naught, and the auto relaxation rate is given by this 2 omega 1 x. So just now I was deriving the rate of population, rate of change in population of P1, P2, P3, P4. So we looked into this, what is this cross relaxation rate and the auto relaxation rate. So this is cross relaxation rate. This is cross relaxation rate. This is auto relaxation rate. So this is 2 omega 1 x plus omega naught plus omega 2. So for small molecules, this ratio comes as half. Now we can also write the magnetization of A, ratio of magnetization of A to magnetization of X is proportional to gamma A and gamma X, gyromagnetic ratio of A and X. So magnetization, we had looked into that magnetization is directly proportional to the nuclear magnetic moment, and nuclear magnetic moment is proportional to the gyromagnetic ratio. So now if we put this one, this Ma naught by Mx naught in this equation, then what we can find, what we will get? So this one, Ma naught by Mx naught into sigma Ax by rho x. So since Ma naught by Mx naught is proportional to gamma A by gamma X, so we can replace this and write this as gamma A by gamma X. And for smaller molecules, for small molecules, we just now saw that this sigma Ax by rho x is half. So this one, this eta the nuclear over the signal that we get from X nuclei when or signal that we get from A nuclei when X nuclei is perturbed is given by half gamma A by gamma X. Okay, is this clear? So what does this say? So for example, if A is proton, consider if A is proton and X is a carbon-13 nuclei. X is carbon-13 nuclei, then the nuclear Overhauser effect will have a value of what? So nuclear Overhauser effect is half gamma A by gamma X, right? Gamma A by gamma X. And what we know that the gyromagnetic ratio of proton is 4 times that of carbon. So if we replace this A and write this 4 times of carbon-13, then what we will get? We will get 2. Right, 4 by 2, that is 2. So we will get an enhancement of 2 if in case of if this AX is for the proton carbon 13 coupling. Okay. Now similarly, if for example A is proton and X is nitrogen 15, then what we will get? Then we will get that the enhancement. What enhancement we will get if this This proton is coupled to this nitrogen 15. Then again we can use this one, gamma proton by gamma nitrogen 15, and we know that the gyromagnetic ratio of proton is 10 times that of nitrogen 15, right? It is 10 times that of nitrogen 15. So if we solve this, we will get an enhancement of 5. We will get an enhancement of 5 in case of if the X nuclei is nitrogen 15. Okay. So what this represents, this one actually represents the maximum NOE obtainable in the system. This represents the maximum NOE obtainable in the system. Okay. Now coming to the transient state NOE. Now this figure shows the pulse scheme. So for understanding transient state NOE, let us look at the figures first. So in the figure on the right, you see that this is the experimental setup, or this is the pulse scheme for the one-dimensional transient NOE experiment. So what is the experiment? So first, the experiment begins with a 180-degree pulse, 180-degree pulse in the X direction. So once this 180-degree pulse is applied on one of the nuclei, what will happen? Its direction will change. Its direction will change. Now we apply a delay of tau m. Delay of tau m, and then so perturbation by a selective 180-degree pulse to invert a particular resonance. Now after this, a certain time period tau m is applied, and this is called the mixing time. And during this time, the spin exchange takes place. Okay. So you have two nuclei, say I and S. So you are perturbing one of the nuclei. First, you are perturbing one of the nuclei with 180-degree X pulse, and now once this is perturbed, its direction will change, and after that, a delay time of called mixing time is applied, and during this time, there will be exchange taking place between the two nuclei. Now the mixing time allows the magnetization to transfer from the inverted spin to other spin via dipole-dipole interaction. So once this 180-degree pulse is applied to one of the nuclei, it will cause this nuclei will invert, and then when this time is allowed, it will cause the magnetization to transfer from this nuclei to the S nuclei via dipole-dipole interaction, and after that, the spectrum is recorded by applying an observed pulse to obtain the on-resonance spectrum. Okay. So, this is a soft pulse, and then this another 90-degree X hard pulse is applied. 90-degree hard pulse is applied to generate to generate the transverse magnetization, and this is then detected as FID, free induction decay. So during the time Tm, the transfer of magnetization occurs from the inverted spin to other spins via dipole-dipole interaction as the inverted spin relaxes back to equilibrium. So during this time, the inverted spin, it will relax back to equilibrium, and this will generate the NOE of the other spin. The time period here is referred to as tau m. Now this one in the transient state NOE, the enhancement that we see is given by this expression, Ni tau m is equal to -1 by mi naught minus 2 m j naught sigma ij tau m. So sigma ij is what? This is the cross relaxation rate, and tau m is the mixing time. Tau m is the mixing time. So what you see that? So here what you can see that in transient state NOE, the transient state NOE is proportional to the mixing time, is directly proportional to the mixing time and the cross relaxation rate. Okay. So there is a lot of matrix algebra that you have to solve to get this equation. So you can find this on the lecture. So just remember that this in transient state NOE, this is proportional to the cross relaxation rate and the mixing time. Okay. So the transient NOE at spin I due to inversion of spin J is directly proportional to the cross relaxation rate between the two spins and is also linearly dependent on mixing time. Okay. Now, what is mixing time tau m? So the transient NOE at spin I due to inversion of spin J. So what we are seeing that you are applying a 180-degree X pulse, 180-degree X pulse to the I nuclei. Okay, 180-degree X pulse is applied to the I nuclei. This will this will cause inversion of one of the nuclei. So for here, what he has said, the transient NOE at spin I due to inversion of spin J. So so in this case, what is happening? So in this case, the 180-degree X pulse is applied to the J nuclei, and this J nuclei will cause this nuclei to cause inversion of the spin of this nuclei, and then time Tm is allowed. Mixing time Tm is allowed, and in this in this mixing time Tm, what will happen? This nuclei J, the nuclei J will return back to return back to its equilibrium position, and also it will exchange magnetization with the other nuclei I. And this one, this one, the transient NOE at spin I. So this is transient NOE at spin I due to inversion of spin J. This what we are seeing, it is proportional to sigma ij into tau m. Now for conditions, what happens is that this mi naught becomes equal to homonuclear case. In homonuclear case, this mi naught becomes equal to mj naught. Mi naught becomes equal to mj naught. So the transient NOE at spin I due to inversion of spin j, it will become 2 ij tau m. Okay, is it clear? So this condition is true for homonuclear case. Homonuclear case means we are seeing so the two nuclei are both the same, that proton-proton. For example, proton-proton is a homonuclear case where mi naught is equal to mj naught, and and also this is true for short mixing time. Now, what is meant by the short mixing time? The short mixing time, how will you determine? How will you find out that how much delay you have to provide so that you see the enhancement effect? So this time should be much shorter compared to the T1. T1 is the spin lattice relaxation time for this nuclei. What is the spin lattice relaxation of this nuclei? That time and that the mixing time should be less than the spin lattice relaxation time. Okay. And also we had seen that this is cross relaxation rate is inversely proportional to the sixth power of internuclear distances, and hence can be used for structure determination. So what does this mean? Since this sigma ij, so just now I've shown you this equation. This one, this one, this one. The spin lattice relaxation. Yeah, the spin lattice relaxation is inversely proportional to the sixth power of the distance between the two nuclei. So that is why the enhancement, the signal that we observed, that can be correlated to the distance between the two nuclei. So we can correlate the signal intensity to the distance that is there between the two nuclei. Okay. Because what we see is that this one is directly proportional to tau m mixing time and also to the cross relaxation rate. And we know that the cross relaxation rate is inversely proportional to the distance between the A nuclei and the X nuclei. So depending on what is the distance between the A nuclei and X nuclei in space, accordingly we will get the signal, and from the signal that we get, we can correlate, we can use it to calculate the distance between the two nuclei. Okay, and this and by doing this, I was saying in the beginning of this session that this NOE is has been used for determining the structure of several macromolecules, starting from like proteins, nucleic acids. So this is why it is possible to calculate the determine the structure of macromolecules. Okay, now we were discussing spectral density. Now we will once again look into what is the spectral density. So what I said previously, that the spectral density is a measure of the molecular motion of the nuclei in the sample. It is a measure of the molecular motion of the rate of molecular motion of the nuclei in the sample. So for large molecules will show slow motion, and since they show slow motion, the spectral density decreases fast. So if you see this graph, so this spectral density versus the frequency, omega frequency, you can find that this for large molecules, the this the spectral density decreases very fast. While for small molecules, the small molecules have shorter correlation time. They have short correlation time. Why they have short correlation time? Because they are tumbling very fast. So their correlation time will be very less. Correlation very less, and but they have much wider frequency distribution. So this is this is shown in this graph that for small molecule which are having small molecular weight, they have a shorter correlation time. They have a shorter correlation time, but the correlation time lasts for a very long time, for a very wide frequency distribution. While for large molecules, they have a very high correlation time, but the correlation time this spectral density decreases very fast. Okay. So this is an example that is there, that for 1,000 Dalton protein. So as we go increase the molecular weight of the sample, or of the, sorry, for example, consider a protein. So for example, we have 1,000 Dalton protein and we have a 10,000 Dalton protein. The correlation time for 1,000 Dalton protein is 0.5 nanosecond, while for a 10,000 Dalton protein it is 5 nanosecond. If you ask that what will be the correlation time for a large molecule, uh, or you can be given a few statements that comment on the correlation, which the correlation time of a large molecule is more than that of a small molecule, or it is less than a small molecule. So, this graph. Understand this graph, and you can attempt these questions. Okay. Now what happens? Now one more thing. Just now we saw that Ni, or the enhancement of nuclei I, enhancement of nuclei I due to inversion of nuclei J for time tau m is directly, it's proportional to what? It is proportional to the cross relaxation rate between this I and J nuclei, and the mixing time So if we continuously increase the mixing time, then what will happen? Will there be a continuous enhancement of the signal that we see? So that is not the case. So if you see this graph, as we increase the mixing time, first the signal, the enhancement of the signal increases linearly, but after certain time, what happens? After certain time, there is the mixing time varies non-linearly. There's a drop in the relaxation time. So higher. So what is it said, that as the mixing time is increased, so as you increase the mixing time, is increased, the enhancement signal becomes non-linear. So higher mixing time is a consequence of the leakage. So why does this become non-linear? So this becomes non-linear because higher mixing time is a consequence of the leakage of the magnetization because of the lattice contribution and various relaxation rate. So as you increase the mixing time, the magnetization starts. There is a leakage of the magnetization to the lattice from the spin. The magnetization starts leaking to the lattice, and this is called spin diffusion. And so after a certain time, we see that the mixing time becomes non-linear. So all measurements must be done in the linear regime, linear regime of tau 1. Okay, so the mixing time should not be increased to beyond this point, at the point at which it becomes non-linear. So all the measurements must be done in the linear the regime of tau m. Okay, so this is for determining. So in transient NOE, what you were seeing that you were that a soft pulse of 180-degree X pulse was given, and then the time of tau m is applied. This delay time of or mixing time is applied so that the magnetization can get redistributed from the X or from the from one nuclei to the other nuclei, or from the nuclei which is perturbed to the nuclei which is non-perturbed. And so this time, how will you determine this time? So you have to consider, all these points and keep these points in mind, that the mixing time is must be less than the it should be much less than the spin lattice relaxation time, and the mixing time should not be very high that it reaches the non-linear. It starts varying non-linearly with the intensity signal. Okay, so these things you have to keep in mind. So based on this, you try to solve this question, that estimation of the distance. How will you estimate the distance between spin E and X by a transient NOE experiment? So what is the requirement? By spin diffusion, short mixing time, large mixing time is independent of the mixing time. So how is mixing time related to determining or estimating the distance between spins A and X in a transient NOE experiment? So what will be the answer to this question? We discussed it just now. So what is spin diffusion? So we discussed that if the mixing time is increased to a very is applied for a very long time. If it is applied for a very long time, then what will happen? Then there will be the magnetization will start leaking to the from the spin to the lattice. So that is called spin diffusion. And what is now the answer, correct answer is short mixing time. Okay, so we have to take care that the mixing time is the mixing time is linearly related to the it falls it comes under this linear portion. Large mixing time results in spin diffusion and is independent of mixing time. That is completely wrong. So the correct answer for this question is option 4. So option 4, what does this? So let's look into the detailed solution. So in a transient NOE experiment, a short mixing time is crucial. This mixing time is the period during which magnetization is allowed to transfer between different spin. A short mixing time minimizes the effect of spin diffusion. Okay, the spin diffusion, that means the leakage of the magnetization to the lattice, that gets minimized if the mixing time is kept short. And if the mixing time is kept short, and helps in measuring the direct in NOE between the specific spins of interest. So in this case, spin A and X before significant spin diffusion can occur. So for accurate estimation of the distance between spin A and X, you want to minimize the influence of spin diffusion and ensure that the NOE observed reflects the interaction between those specific spins. So the main, so what you have to keep in mind that we want to minimize the spin diffusion. We want to keep the spin diffusion as minimum as possible, and for this, the mixing time has to be kept low. You have to keep a short mixing time and ensure that the observed reflects the interaction between those specific spins. A short mixing time achieves this by capturing the NOE effect before it gets complicated by the diffusion process. So the NOE effect must get transferred to the other nuclei S nuclei. So we have to ensure that the mixing time is not so long that before that this NOE effect, rather than getting transferred to this S nuclei, it is getting leaked to the lattice or the and or we can say that lattice is what is the environment outside the nuclei. So all the environment leaving aside the nuclei, nuclear spins are the other is the lattice. Okay. So now we will talk about the inept technique. So now what we have seen in selective population inversions. In selective population inversion, so we will talk about the selective population inversion in a bit. We'll revise this concept, selective population inversion. So if we consider a two-spin system AX, so X represents a heteronuclei. Here what does X mean? X represents a heteronuclei. Heteronuclei, and A represents proton. Okay. So consider that in an AX system, X represents the heteronuclei. It can be anything C13, N15, and A represents the proton. And now if we draw the energy level diagram, then what we draw the energy level diagram of this AX pin system. So, so there are consider that this is the population. So in the equilibrium, they will have the same population. So these are the four energy levels: 1, 2, 3, 4. These are the four energy levels. So the transitions. Let us indicate the transition from 1 to 3, from 1 to 2, from 2 to 4. These are the transitions, and so these are the populations of the and different in the different energy level. In the energy level 1, the population is del plus del. This state it will have del minus del, or you can also write it minus delta. This triangle minus this one. So this is for A1, 2. This is X1, this is X2. Right. Just a second. So what does this energy diagram what does it show? It shows that it represents the four energy levels: 1, 2, 3, 4 of two-spin AX spin system, and this delta and del are used to it represents the populations of these different energy levels. And the now what we will do is so E2 is the transition from 3 to 4, right? A1 is the transition from 1 to 2. X1 is the transition from 1 to 3, and X2 indicates the transition from 2 to 4. Okay. Now intensities of A1 and E2 transitions are 2 del each, right? A1 and E2 transitions, if we see what are the intensities, then what will be that? So it will be, so what will be the intensities? Delta minus delta plus L minus del or they are 2 del each, and similarly intensity of the X transitions are 2 delta each. Okay, so this is for X1 and X2. So if you basically if you subtract this one delta plus delta, so it is 2 del. And the intensities for A1 and A2 transitions are what? This is 2 del and 2 del. So if you subtract this one, delta plus delta minus, so be delta. So it will be 2 delta. Okay. Now what happens? Up 180-degree pulse is applied to the A1. So I've shown this one actually. Yeah. So the problem so if you look at this figure, so this is actually the figure for selective population inversion. So now what you are doing is you are so in the equilibrium state, this is the intensity of X1 and X2 are 2 delta each, and the intensity of A1 and A2 are 2 del each. Now what you are doing in this case is that you are applying a 180-degree pulse to the A1 transition. You are applying a 180-degree pulse to the this one. So here in arrow, what it indicates that you are applying a 180-degree pulse to the A1 transition, and as a consequence of this, so whenever a 180-degree pulse will be applied to this A1 to this A1 nuclei, A1 transition, the populations of level 1 and 2 will get interchanged. The population of A1 and 2 will get interchanged, and in this scenario, the intensities of the X1 and X2 transitions will become minus 2 del minus 2 this one. Okay. And for X1, this will be this one. And for X2, it will be 2 delta plus 2 delta. So clearly there is a substantial change in the intensities of the X transition if one calculates the change in intensities of the two transition from the equilibrium. So this was the equilibrium condition. So if we calculate that what is the change in intensity from the equilibrium condition, then what we will then this is a large change. Okay. So what happens? So here you can see that this one was like this, and then when this 180-degree impulse is applied, then there is inversion of this population. So X1 becomes this one, and A1 becomes this one. Okay. So there is an intensity gain of so there is an intensity gain, right? Now, what is happening in inept? So this is the pulse sequence of inept. Okay. So this is the pulse sequence of an inept experiment. So in an inept experiment, what is done? First, a 90-degree X pulse is applied. Then a delay of tau is given. Then a 180-degree X is applied. So this is one for spin A. For spin A, first a 90-degree X pulse is applied to spin A. Then a delay of tau is applied. Then again a 180-degree X pulse is applied. Then a delay of tau, and then 90-degree Y is applied. So basically inept. First of all, let us understand what is inept. So inept is insensitive nuclei enhanced polarization transfer. What is inept? It is insensitive nuclei enhanced polarization transfer. And what is done in this technique? So in this technique, what is done is non-selective pulses. This technique uses non-selective pulses for transfer. Okay. So the basic pulse sequence of this inept sequence, I was showing that it was 90-degree X followed by a tau, then another 180X, then again a tau, and then 90Y. Okay. So, let's look at the vector diagram of this pulse sequence. Let's look at the vector diagram of this pulse sequence. So what happens is first 90x pulse on the first 90-degree. So this is the A nuclear spin. A 90-degree X pulse on the A spin is applied, and this pulse causes the A spin, the Z magnetization of the A spin to rotate to the minus Y axis, right? So the 90-degree first, this 90-degree X pulse that is applied on the A spin, it will cause the magnetization to move from the in the equilibrium position, it is in the Z direction. It will cause the magnetization to shift to the minus Y direction. Okay. Now next, what happens? Next, a 1 by 4j time period is applied. Now in this 1 by 4j time period that is applied, these the two nuclei A1 and A2, they will start moving in opposite direction. Okay. They will start dephasing out, and they will start dephasing out. Now again, then after this 1 by 4j time delay, a 180-degree pulse is applied, and this 180-degree pulse, what it does, it completely it completely changes the direction of the spin of A nuclei and A2 nuclei. Okay. Then again now 180-degree X pulse is applied. So after this one, so this is 1, 2, 3. Then a 180-degree X pulse is applied to the X nuclei, and when this is applied, this will again start moving in the opposite direction. Now this again this time delay of 1 by 4j is applied, and in this time delay, the magnetization moves from the y axis to the x axis, to the minus x axis, and then a 90-degree pulse is 90-degree Y pulse is applied to A, and this causes the magnetization to move to the completely to the Z axis. And then a sequential 90x pulse is applied, which causes this X1 and X2 nuclei to the spins become oriented in two different directions, and then their FIT is detected. So since these two nuclei come in two different directions, you can see that one is above this above remains this in the positive direction, and another remains in the negative direction. Okay. So let's understand this pulse sequence. So 90-degree X pulse on the A spin rotates the Z magnetization of the A spin to the minus Y axis. Okay. So 90-degree X pulse is applied on the A spin, and this causes the A spin to the Z magnetization of the A spin to move to the minus Y axis. Then what is that? During the next tau equal to 1 by 4j period, these two components will dephase out. They'll dephase, and they will dephase to the extent of 90-degree phase difference. Now after this, a 180-degree X pulse is applied on the A transition. Now once this 180 X pulse is applied, the two transitions will move in the opposite quadrants. It will start rotating in the opposite quadrant, and similarly simultaneously a 180-degree pulse on the X nucleus is also applied. So A transition is 180-degree X pulse is applied on the A transition, and simultaneously a 180-degree pulse is also applied on the X nucleus, and this 180-degree pulse, it interchanges the labels of A transitions, as a result of which they continues to dephase further. And so here what you saw, that once this after the 180-degree X pulse is applied on A, it starts to it moves to in the opposite direction, and then simultaneously a 180-degree X pulse is also applied. So here you can see in this pulse sequence, so 180-degree X pulse is applied to the A nuclei, and simultaneously a 180-degree X pulse is applied to the X nuclei. And this, when this 180-degree X pulse is applied, so it will, what will happen? It will interchange the labels of A transitions, as a result of which they continue to dephase further. And at the end of next 1/4J period, they're aligned in opposite directions along the x-axis. So you see over here that after 1/4J time period, they align in opposite direction on the x-axis. Okay, in the opposite direction in the x-axis. Now what happens? Now a 90-degree Y pulse is applied on the A spin. And when the 190-degree Y pulse is applied on the A spin, the spin will move along the plus Z and plus X axis. So so this has oriented in the minus X and plus X direction. A1 is oriented in the minus X direction. A2 is oriented in the plus X direction. Now a 90-degree Y pulse is applied on A, and this will cause the shift of the X magnetization to the Z direction, right? To the Z direction. And now from moving, now we have to now we have to move this magnetization Z to the X axis. So now a 90-degree X pulse is applied. In the direction of x-axis, another pulse is applied, and the following 90-degree pulse put this the following a final 90x pulse on the X channel. The signal is detected, and then we detect the signal, and then this signal is Fourier transformed to get to convert this frequency domain to time domain, right? So this is clear inept experiment, that is insensitive nuclei enhanced polarization transfer. So first a 180-degree X pulse is applied. A 180-degree X pulse is applied on A transition, and when this is applied, both the transition, this A1 and A2, both these transitions will move to the minus Y axis. Now a delay of 1/4J period is applied, and this 1/4J period, what will it cause? It will cause the two components to dephase. So this starts dephasing out, and they will dephase to an extent of 90-degree phase difference. And then a 180-degree X pulse is applied on A transition. Now, when this 180-degree X pulse is applied on the A transition, it will cause the interchange in the. So here, this one A2 will come to interchange in the label. So A2 will come here and A1 will come here, right? So this one, yeah. So it will cause. So it will completely shift to this one. There will be interchange between them, and then again, and then simultaneously, a 180-degree X pulse is applied on the X nuclei. Is applied on the X nuclei, and this 180-degree pulse will cause this A1 and A2 to in the plus Z and minus Z axis. Okay. And after this, so this one, then 90-degree X pulse, wow, Y pulse is applied. So this moves the X to Z, and then again a 90-degree X pulse is applied. This will cause the Z to move to the minus X. Okay. So this scenario is equivalent to a selective inversion of one of the A transition, and so that we described previously. Now try answering this question in an inept experiment. Polarization is transferred from sensitive to insensitive nuclei. The option B is polarization is transferred from insensitive to sensitive nuclei, and the third option is transfer efficiency is independent of the type of nuclei, and there is no gain in the sensitivity. So here the answer is already given. I forgot to add an animation. So these are all polarization transfer experiments. So okay, so in polarization transfer experiment, what happens that we have a the less sensitive nuclei and we have a high sensitive nuclei, and the signal is transferred from always from the less sensitive nuclei. From the more sensitive nuclei to the less sensitive nuclei. So for so we as we had discussed, as it was discussed in the lecture, that the sensitivity of the nucleus depends on the gyromagnetic ratio, and the carbon 13 is a less sensitive nuclei. So if you want to study the signal, or if you want to see the signal of less sensitive nuclei, then we carry out this polarization transfer experiments, in which what we do, we perturb the nuclei of the we perturb the the more sensitive nuclei, and this polarization gets transferred to the less sensitive nuclei, and in this way we can enhance the signal that from the less sensitive nuclei. Okay, so INEPT also works by the same principle. It works by transferring the polarization. Yeah, so the correct answer is it's transferred from the, so just now we were seeing H1C13 and all those we were seeing that in NOE that it is a ratio of the gamma A by gamma X. Okay. So INEPT works by transferring polarization from nuclei that are less sensitive or insensitive to nuclear that are less sensitive or that are insensitive, and this polarization is transferred to where it is transferred to nuclei that are more sensitive. And this method enhances the signal of the sensitive nuclei by effectively transferring polarization to them from the less sensitive ones. Okay. INEPT uses non-selective pulses and specific pulse sequences to achieve efficient polarization transfer from less sensitive nuclei to more sensitive nuclei. So, for example, C13 is a less sensitive nuclei, more sensitive is proton. So, it uses non-selective pulses. So, we perturb one nucleus, and the polarization is transferred to the other nuclei. And in this way, the polarization gets transferred from the less sensitive nuclei to the more sensitive nuclei. This results in a significant increase in signal intensity of the sensitive nuclei, which is advantageous for obtaining clearer and more detailed spectra. Okay. Now we will discuss one last concept of today's session. In today's session, that is the refocused inept. Okay, so what we were seeing in inept is that the signal for X2 and X3, one was coming positive, one was coming negative. So what is done in refocused inept is that to remove these negative values, another pulse sequence is given that is equivalent to the spin echo pulse sequence. So after this inept pulse sequence, another pulse sequence, which is the spin echo pulse sequence, is given, and this spin echo pulse sequence. So this spin echo pulse sequence will cause the this negative to shift to the positive component. Okay, so basically it helps to refocus the positive negative components. So after this one was the last one, right? So we have seen this one. So 90-degree, yeah, 90-degree Y pulse and 90-degree X pulse. And after that, another pulse sequence of this one. 180. So yeah, you know the pulse sequence of spin echo we had discussed in four. Week 4, I guess. So in the spin echo, we said that the pulse sequence is 180 x tau 90. So that one was the spin echo pulse sequence. So after this 90, so the last 90-degree pulse in the pulse sequence removes some artifacts and results in clean multiplets in the spectrum. So what you see, so compared to this, you are seeing clean multiplets in the spectrum. Okay, so try to solve this question that for a CX spin system with one bond coupling of 125 Hz, the refocusing delay should be. So what try to solve this question, 8 millisecond, 4 millisecond, 2 millisecond, and 1 millisecond. So with one bond coupling, so the bond coupling is given. So bond coupling means J. J of C of H is given as 125 Hertz. So what will be the refocusing delay? So what is refocusing delay? So the refocusing delay is it will be applied to refocus the two spins that were oriented in different direction. So this we had seen tau is one. So actually the refocusing delay is given by the formula 1 by 2 tau. Refocusing delay, this is given by 1 by tau is equal to 1 by 2j. 1 by 2j. Okay, so it is twice the bond coupling of the two spin system. So here the two spin system, this C and GH. This C and GH, it has a bond coupling of 1 by 2 of 125 hertz. 125 hertz. So you put this equation, and this will be how much? So if you calculate this and tell me the answer. You can. So this will be 0.004 second, or it will be how much? It will be 4 millisecond. It will be 4 milliseconds. So let us look at the solution. The correct answer is option B, which is 4 millisecond. The refocusing delay in the NMR sequence is often related to the coupling constant. So the coupling constant is given in this question. It is 125 hertz. It is related to the coupling constant, and it is designed to be half the period of the coupling constant frequency. Okay, so the coupling constant frequency is 125 hertz, and the refocusing delay is given as it is related to the coupling constant as half of the coupling constant, half of the coupling constant. So yeah, so you can solve this. So this has been solved for a coupling constant j of 125 hertz. The period will be what? It will be t equal to 1 by j. 1 by 125 second, it will be 8 millisecond. But the refocusing delay, so this will be the what will be the refocusing delay then? The refocusing delay used in pulse sequence will be half of this period. Half of this period to refocus the magnetization properly. And so the refocusing delay is tau equal to t by 2 or 4 millisecond. Okay. This was the last question of today's session. So I hope this session proved to be useful. If you have any more doubts, you can ask me, and we can take up any other question that you faced while solving your assignments. So what all did we discuss today? So today we discussed about this. So let's have a quick recap. So we looked at the nuclear overhauser effect in more detail. So first of all, we tried to understand that once after the perturbation, when the magnetization relaxes, what is the what will be the change in population of the different states. So if it is AX system, so we saw that the AX system has different states. It has four states: alpha alpha, alpha beta, beta alpha, beta beta. So how is the population? How is the population in these three energy levels, or in these four states changes over time? So how is that given? So this is given by this equation, and then using this equation, we derived that how will the population change? How will the population change in the energy levels 1, 2, 3, and 4? So we had four energy levels. So how is the population in these four energy levels are changing with respect to time? We revised a few concepts that were already discussed in the last lecture related to nuclear overhauser effect. And Yeah, so we derived the different rate equations, the rate equations for various population changes, DP1, DP2, DP3, and then what we found that that these populations are also related to the magnetization of spin A and X, and so how is the magnetization related to the population? So the magnetization of the A spin and the X spin in the equilibrium condition is related to the population in by this equation. Okay, so P1, P2 we had already discussed. So this one was P1, this one P2, P3, P4. P1, P2 was what? P1 to P2 was what? A1, A2, X1, X2. Okay, so what will be the magnetization of A? So magnetization of A will be this one P1 plus P2 minus P3 minus P4. And the magnetization of X will be P1 plus P3. So this is just they have it is written in a rearranged form. So this is nothing. This is P1 plus P3 minus P4 minus P2. Okay, so that is all. Now, so that so it is written so that these two looks it, it can be easily correlated, so in a sequential order. Now if we solve this equation and if we differentiate this with respect to time, what do we get? We get that 2W1A plus this equation we get, and this one is 2W1A plus omega naught plus omega 2. This is called the auto relaxation rate. This is called the auto relaxation rate, that is auto relaxation rate rho of A. And this is called the cross relaxation rate of AX. This is the auto relaxation rate of AX, and this is the factor. This omega 2 minus omega naught. This cross relaxation rate determines what signal we will obtain in the NOE experiment. So if omega 2, so in case of positive NOE, what do we for positive we get positive NOE for small molecules and we get negative NOE for large molecules. So in case of large molecules, we get negative because this zero order quantum transition operates more efficiently. And in case of small molecules, we get positive anyway because this omega 2 is more than omega naught. So this actually this cross relaxation rate determines this whether it will be what will be the signal that we obtain. Now we also looked into how this nuclear Oberhauser effect is related to time. So it is how so the nuclear Oberhauser effect is dependent on how what are the rates of molecular motions in the sample. What are the how are the different nuclei? What is the tumbling time of different nuclei? And this tumbling time, and this one gives us the spectral density. So this uh, correlation time versus the enhancement signal that we see. So see what we important point to remember over here is that for a small molecule we have positive NOE, and for large molecules we have negative NOE, and the large molecules have a longer correlation times and the small molecules have a shorter correlation time. So all these transition probabilities are related to the correlation time. So these are the different equations you not need to memorize, and this is a K is a constant, and it is inversely proportional to inversely proportional to the sixth power of the distance between the A nuclei and the X nuclei. And also we looked into this question. So spectral density is basically what it is a power distribution as a function of frequency due to molecular motion. So due to molecular motion, the power distribution that we see is called the spectral density function. Then we looked into the steady state NOE. So in steady state NOE, what happens is first a 180-degree X pulse is applied, and then the short time is applied. In this short time, there is exchange in the magnetization, and then a hard pulse of 90 degree. No, So sorry for in a steady state NOE, first the one of the nuclei is saturated. First one of the nuclei is saturated. This causes equal proportion of population in both the states, and then a 180-degree X pulse is applied, and then following a 90-degree pulse, we record the FID. Okay. So we derived that for small molecules. For small molecules, this enhancement enhancement is related by half gamma A by gamma X. So gamma A can be anything. You can consider proton. X can be considered as carbon, and then you can calculate the enhancement signal for the two nuclei that are coupled. Then we look into transient NOE, right? Steady state NOE was this one. I've kept the figure. Yeah. So yeah, this saturation, then 90-degree X pulse is applied, and then we are recording FID. But in case of transient NOE, a 180-degree X pulse is applied, and this inverts the particular resonance, and then at mixing time tau m is applied, and then again a 90-degree X pulse is applied, and then the FID is recorded. And we saw that this one in transient state NOE, the enhancement signal is proportional to the cross relaxation rate and the mixing time, and the cross relaxation rate is inversely proportional. This cross relaxation rate is inversely proportional to the sixth power of the internuclear distance between A and X nuclei, between the A and the X nuclei. So yeah. So in case of homonuclear case, we derived this expression, and we also found that this the mixing time must be shorter compared to the spin lattice relaxation time, and the cross relaxation rate is yeah. So that's what I discussed, and then we look into the spectral density. So for large molecular weight, the spectral density decreases very rapidly, but for small molecular weight protein, they have a shorter smaller correlation time, but it has a very broad range of frequency. But this correlation time lasts for a very broad range of frequency. Then we looked at this point that mixing time. This mixing time should be uh, must fall in the linear region of the signal enhancement. Otherwise, it will lead to what? Spin diffusion. So in spin diffusion, if you apply a very long mixing time, then what will happen? The magnetization gets leaked to the surrounding lattice. Gets into the surrounding lattice. So it should be applied in the for a short time. Okay. And then we looked into the inept experiment, which is what it is. Insensitive nuclei enhanced polarization transfer. It is also the type of polarization transfer experiment. And we looked at the pulse sequence and what is the pulse sequence, and also we looked at the vector diagram of how the pulse sequence causes a transition of this magnetization. Okay. And we looked at in the last part of the lecture, we looked at the refocused inept experiment. Okay. So that was all for today. Okay. Yeah, so that the session proved to be useful, and we will take up more questions and understand more concepts in the next lecture. Okay. Thank you, everyone.